Okay, so continuing on with this chapter, we'll next go on to Ampere's law. So, to put things in perspective, we way back at the beginning talked about Coulomb's law, which told us what the force would be between two charges, and then we used a kind of form of Coulomb's law to talk about the electric field. So the electric field existed with just one charge. If you had a second charge, then you could talk about the force. But we want to just talk about some point charge and the field around it, and we use some form of Coulomb's law to describe that. And if you remember, if you had some charge distribution about some surface or something, that could be a very difficult thing to do to integrate and derive this expression for the magnetic field at some point due to a distribution of charges. So then we discussed this idea called Gauss's law, where it said that the electric flux through some closed surface is proportional to the charge enclosed by that surface. And what that did was that gave us a way of calculating the electric field in a very simple way if there is sufficient symmetry. We had to match that Gaussian surface to the symmetry of the charge distribution. And if you could do that, if there was sufficient symmetry, it was a kind of trick of making the math really simple to calculate the electric field. Well, we're going to do the same thing here. It's all analogous. We use Biot-Savart's law, that complicated integral formula, to calculate the magnetic field due to some current. Some could be some arbitrary wire waving around in space, and we'd have to do that complicated integral, but we could do it using Biot-Savart's law to calculate the magnetic field at some point in space. But now we're going to say, what if we have sufficient symmetry? We can do a trick kind of like Gauss's law. That trick is Ampere's law. So it's a shortcut that links magnetic field to current. So let's say you have some current and you draw some arbitrary closed path around that current. So we're looking at an arbitrary closed path. It could be of any shape. This is an irregular shape. Now, in reality, we're going to have to apply symmetry considerations here in how we define the closed path, just the way we did with Gauss's with the Gaussian surface. But for the time being, it's just any arbitrary closed path. Let me shrink my face here. So if we look at what we will call a path integral, which is we're looking at the projection of the magnetic field that is parallel to the path. So at any point in space, let's say the magnetic field is this way, but your path is moving along this way. We want to know what is the projection of B onto that path, and we call that B parallel. So how much, in other words, what we're saying is how much of that magnetic field is along the direction that we're traveling in this path. And keep in mind these two vectors, I mean, it's going to constantly change because as your path weaves in and out, the projection of the magnetic field onto that path is going to change. This process is called a path integral. And it finds the way we would do that is to take the dot product, because remember, dot products are the projection of one vector onto another. So this looks very similar to flux. It's not flux though, because this is a path integral. We're integrating along some closed path ds, where we start one place and we go all the way around and come back to where we started from. Flux is integration over a closed surface. So very different thing. And this little circle means that it's a closed path. We go all the way back and come back around. And Ampere's law says that this path integral of the magnetic field over some closed path is equal to a constant, mu naught again, times the current. And here the current is that which is piercing the surface mapped out by the path. So if we take this closed path all the way around, we come back, we've got this disc-like surface, and however much current is piercing that surface goes here. So just like with Gauss's law, we had electric flux equals the charge enclosed, and you had to remember that was the charge enclosed by the Gaussian surface. Here we have the path integral about some closed path is going to be proportional to the current piercing the area mapped swept out by that closed path. That is Ampere's law. So if we want to apply Ampere's law for a long straight wire, we will use a closed circular path. Why? Why not that arbitrary wavy path that we saw before? Well, that's because we're trying to match up the symmetry of the magnetic field. And we know that the magnetic field lines are going to circle around this current carrying wire. So we're going to choose a path. I guess you could say an Amperian loop is how we often refer to it. We choose an Amperian loop that matches the symmetry of the magnetic field. So it's going to be circular. The circumference of that circle is 2 pi r. Hope you all remember that. So since the magnetic field is constant and is always in the same direction as ds as we go in its infinitesimal pieces around the path, remember ds is going to be tangential to the curve at every location all the way around. Well, the magnetic field is also tangential everywhere around, so this dot product goes away. Or you could say b dot ds cosine of phi, but phi is always 0. And the magnetic field is constant because you're at a fixed distance away from the wire, r. So we can pull b out of the integral, we can integrate ds, and the circumference is 2 pi r, so as we integrate ds around that whole circle, 2 pi r comes into the equation. And this is where this is where Ampere's law comes into play. This path integral is now equal to mu naught I, where I is the current piercing this circular disk mapped out by the path, the Amperian loop. Solve for the magnetic field. We have the magnetic field B is equal to mu naught I over 2 pi r. That's exactly what we saw earlier, except last time instead of r we used A. But it's the same thing, and we've done it. We've recaptured what we expected to get. If you remember with Gauss's law, we did the exact same thing. We drew a Gaussian surface around a point charge and applied this neat, nice symmetry to the problem, and we found that the electric field was just the electric field of a point charge that we expected. So we're following the same pattern here.
Okay, so this problem involves Ampere's law, which says that the line integral or path integral of B, let's ignore that. The path integral of B dot ds, that means the integral of the magnetic field B along the path ds, is equal to mu naught I. I should also note that part of Ampere's law says that this path integral must be performed along a closed loop. So for the first part of the problem, we're given the radius of this wire, we're given the current through the wire, and we want to find the magnetic field at some point. First, let's find some point P where r is greater than the radius of the wire. So you're out here somewhere on the wire, and you want to find the magnetic field right there. Well, this, okay, so I'm going to draw the wire again, R. This holds true no matter what shape you draw. I can draw it, I probably shouldn't loop over myself there, but I can draw whatever shape I want, and as long as I perform this integral, this will hold true. But it makes no darn sense whatsoever to draw a weird shape like this because you're trying to take advantage of symmetry. This is very analogous to Gauss's law. What kind of symmetry are we taking advantage of? Well, if I draw the wire again, and let's say I use cylindrical symmetry, because remember this is a 2D projection of a three-dimensional thing. But anyways, it's 2D symmetry. At any point P, the magnetic field is going to be in this direction, right? Because we know this already, that the magnetic field circles around the current. So as I move all along this path, at any point in this path, the direction of ds, the little segment of the line moving in the direction of as we move around that closed loop, is always going to be in the direction of B. And B will be constant at every point along that circle. We know that already from what we talked about, the empirical results of the measurements that Biot and Savart did, and they came up with the Biot-Savart's law, and they found that the magnetic field dropped off in magnitude with 1 over r squared as you got away. We know already that at any fixed distance away from the wire, the magnetic field is going to be constant. So that is why we draw this symmetric thing, the symmetric Amperian surface, if you want to call it that. So that means since B is constant all along the closed loop, we can pull B out of the integral. And we also know if we integrate around that closed loop, B is just 2 pi r. Because remember, we're not talking about the area here. It's not dA, it's ds. We're integrating the path. We're integrating the path along this circular route. So that is the circumference of the circle, and that just equals mu naught I. And I should say I enclosed, just to indicate that it's not really enclosed. It's the current passing through this loop. I don't like to use the phrase enclosed because that works with Gauss's law, because Gauss's law has a Gaussian surface, so the charge actually is enclosed. In this case, the current is just passing through. Maybe I should say through. So that means the magnetic field at any point r, where r is greater than the radius of the wire, is going to be mu naught I through over 2 pi r. Well, that's just as expected, because we already found the same result with the Biot-Savart law. The difference is that Biot-Savart's law was really complicated. If you remember, we had to find at some point P, we had to integrate ds, theta 1 to theta 2. We had to integrate all along that line. It was a really complicated result with the Biot-Savart's law. That's because this is a brute force method of calculating the magnetic field. This is a trick that makes things a lot easier. Okay, so let's now go down to the next part, which is find B at r is less than the radius of the wire. What that means is r is inside the wire, because yes, there's going to be magnetic fields inside of a wire. This gets a little more complicated. We go back to Ampere's law, B dot ds equals mu naught I through. Just like before, it's going to be constant all around, so we can say B times 2 pi r because of the symmetry, right? If the current density is uniform, let's assume uniform current density. So then we can say exactly like we did here, B times 2 pi r equals mu naught I through. But what actually is the current running through there? Well, we know that let's say we take a ratio of I at r over the total current, and I'll call that I sub big R, because big R is the radius of the wire. Well, we know that's going to be proportional to the area because we're assuming uniform current density. So the area of that this current passes through is pi r squared, and the area that this passes through is pi capital R squared, because this is the whole cross-sectional area of the wire. So that means I through, that I'm calling it, is equal to IR, because that's going to be the current through this Amperian loop is going to equal the current IR, which is equal to, cancel out the pi's, R squared over capital R squared IR, where IR is just this current we're given in the beginning, the total current through the wire. So then I can say B is equal to mu naught I through over 2 pi R, which is equal to mu naught over 2 pi R times I through, which is R over R squared. I just rearranged that. Times the total current, I sub big R, I'll just call it I, because that's what we're given and asked for in the problem. Okay, so I can simplify some stuff. B is equal to mu naught I over 2 pi R squared times R. So if we graph it, B as a function of R, well, R at 0 is going to increase up to the point where R equals R, the radius of the wire, and then it's going to decrease proportional to 1 over R, and this is proportional to R. So it increases linearly, and then it decreases at the rate of 1 over R. Once you get inside wire, outside wire. This problem is an application of Ampere's law that I hope shows you the usefulness of it. In this situation, and I'm calling this loop side A and side B, where A is equal to 20 centimeters and B is equal to 15 centimeters. Those are the dimensions. In this problem, you have a magnetic field, a uniform magnetic field that points to the right, and then it uniformly switches, it abruptly switches and points to the left. And so the question asks us to find the current encircled by this loop. So I'm going to first label all the sides. Let me use the convention I used before. So I'm starting here, 1, 2, 3, 4. Side 1, 2, 3, and 4. Why is this useful? So let's say you have a very complicated situation. Let's say you have a current running through a wire, another wire, here's a wire running the opposite direction, here's another one running out of the page, here's another one running in the opposite direction. This is not necessarily going to match this electric field, but if you wanted to just find out what is the total current of all this stuff, you could put a loop around it, use Ampere's law, and by the magnetic field, you could find the current inside there. So, for example, those clamps that measure the current through a wire by clamping around it, it's doing basically the same thing. It's measuring the electric field at all points around it, and then back calculating the current. But anyways, if we start with Ampere's law, the line integral or path integral of the magnetic field B along the path ds integrated is going to equal mu naught times the current through the path that the closed path that you laid out. Well, we can do this segment by segment, 1, 2, 3, and 4. But we notice something immediately, right? Let's look at side 1. So this is the path S, and this is the little portion of the path ds, and this is the magnetic field B. what do we notice about the two are at right angles? So the integral of b dot ds equals 0 because b is perpendicular to s, or to ds, I should say, because you're integrating, but it's a straight line, so it's going to become this. So this is the same for side 3. Same situation. The magnetic field is pointing this way, and you're integrating along this direction. Now, even though the magnetic field switches at some point, it's always perpendicular. So that equals 0. So for side 2, you have S in this direction. Why in that direction? Well, I'm just choosing to go in that direction. I mean, I could choose to go whatever direction around the loop I wanted, as long as I was consistent the whole way around. Because the magnetic field is in this direction, I chose to integrate along this direction, come back, and then go back the other way along side 2. So the magnetic field is this direction. So if phi is the angle between those two vectors, then cosine of phi is 0. So B, I don't know, we're going to call it B2. What now? B ds2 is just equal to the integral along the closed path. Well, it's not a closed path because I'm doing it segment by segment. So I'm going to take the little circle out because it's not a closed path anymore. I should have done the same thing up here too. I'm being really picky about notation, but we have to be. So this is just equal to b dot ds. And you notice the magnetic field is the same at every point along here, so you can pull b out of the integral. It's just b times the integral. Once I integrate this, this is just bs2, which is equal to b times a. The path distance is a. So if I go now to side 4, this side, so I'm now moving in a different direction, but I'm still moving in the same direction as the magnetic field because the magnetic field changed direction. So there's no negatives or anything to deal with. Cosine of phi, the angle between those two vectors, is still 0. So the integral of b dot ds for the cosine phi is 0, so this is just b times ds4. The magnetic field is constant everywhere on that path, so I can pull b out of the integral. So this is just the integral of s4. So that's b times s4. S4, just this path from here to here, is just ba. So then pulling it all back together, Gauss's law says that the integral around a closed path, remember that circle means around a closed path, of b dot ds, where the b is the magnetic field all along that closed path, s is the path itself. That's going to be the integral of b ds1 plus the integral of, I should put the dot product in there, b dot ds1 plus the integral of b dot ds2 plus the integral of b dot ds3 plus the integral of b dot ds4, and according to Ampere's law, that equals mu naught I through. Well, we know 1 and 3 are 0, 0. So all of these integrals together add up to the integral around the closed path. So this equals the integral of b dot ds2 and b dot ds4, which is just ba plus ba equals mu naught I enclosed, or we're looking for I. I said I enclosed, it should be I through. I'm just trying to differentiate from Gauss's law. So I through is equal to 2ba over mu naught. If you put in the numbers, that's 2 times 75 times 10 to the negative 6th Tesla times A 0.20 meters over mu naught, which is 4 pi times 10 to the negative 7th newtons per ampere squared. I through then is 24 amps.